Hello and welcome to Lecture 5, where we'll be discussing Kirchhoff's voltage and current laws. Specifically, the contents are a bit of motivation and history behind these laws, Kirchhoff's current law or KCL, Kirchhoff's voltage law or KVL, numerous examples, as well as a quiz as usual. So let's dive right in. So a bit of motivation. So what have we learned so far? We've learned Ohm's law, which relates the voltage, the current, and the resistance of an element. Specifically, it relates the current through the element as well as the voltage across it. But suppose we have a circuit as shown in the bottom right. We have a couple of elements, an independent voltage source, an independent current source, and we could have also had dependent sources. But here are the questions here. If we're going to extend our toolkit and move forward with circuit analysis techniques, we have to ask these questions. What are the values of the voltages V1 through V4, shown here with the polarities indicated? What are the values of the currents I1 through I4, indicated in the orange? What are the true polarities of each voltage drop or rise? And what is the true direction for each current? So these last two questions are very important because if you recall, to be able to correctly calculate the power dissipated or absorbed, power absorbed / dissipated or sourced by an element. So if you have an element, so if you have a voltage source connected to an element, we're going to have some current flowing through it and some voltage drop across it. Now the question is, given that the voltage drop is given in this direction and the polarities are indicated as such, and that is the true polarity, is the current going to flow this way or in the other direction? So recall from passive sign convention that if the current flows from the high potential to the low potential, we're going to have P is equal to I times V, which is going to be some quantity, and that's going to be in watts, and it's going to be a positive quantity because we have two positive quantities multiplied by each other. But if you have the current flowing in the opposite direction, let's indicate that in red, that's I star, you could say. What's going to be my answer? So now we're going to say that P is equal to minus I star because the current is going from a lower potential to a higher potential times V, which is going to be in watts, and it's going to give us a negative quantity, which means that that element is sourcing power, or it's giving power to the rest of the circuits or circuit which is consuming that current, whereas here we're dissipating or absorbing, you could say, absorbing. Okay, with that reminder in place, it shows why it's important. It shows why these two questions are very important, because if you have the incorrect polarity for the voltage or the direction of current, we're going to get the incorrect assumption about power absorption or power sourcing into the circuit, and therefore we're not going to satisfy the law of conservation of energy. And if that's not conserved, it means that the circuit is not correctly analyzed or set up. So now that we understand the motivation and we understand the importance of where we're at, let's answer these questions. These 4 questions, we're going to answer it now with the toolkit that we have, which is Ohm's law. And here's the answer. We don't know. With Ohm's law, we're not able to relate the voltages and the currents in a given circuit systematically. So whereas we could find the current or the voltage through or the voltage across a single element, a resistive element that is, we're not going to be able to just apply Ohm's law here and find or relate the voltages and currents in a systematic way, which means we do not thus far have the capability to analyze larger circuits containing more than one resistive element in them. So with that being said, let's go ahead and introduce Kirchhoff. So Kirchhoff to the rescue for this deficiency. So who is Kirchhoff? So Gustav Robert Kirchhoff was born in Königsberg, Prussia on March 12, 1824, and unfortunately he passed away in October 17, 1887. Now this man contributed to physics as well as electrical engineering. He contributed in terms of spectral analysis, and what is important for us in this lecture series is circuit analysis or circuit laws that will help us perform circuit analysis. Okay, so now let's move on and talk about Kirchhoff's current law, or KCL. So KCL says that the algebraic sum of currents leaving or entering a closed region is 0. Or to look at that mathematically, it says that the sum of the currents from m equals 1 to n, or to write it more nicely, to write it more obviously, I1 plus I2 plus I3 plus dot 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 plus I sub m is equal to 0. So what this is saying is that mathematically it's telling you that every current entering or leaving a given region, the sum of them must equal 0. So to get a picture for that, here we have 3 different branches connected at one node, and we have the region shown in yellow. And in this example, I have I2 entering and I1 and I3 leaving this region or this node. Now keep in mind that you can say a node is a region because it's as if you've shrunk a region down into a single point, and that would be a node. So from now on, we're going to be talking about nodes and not regions. Regions are more for electromagnetic problems that are not lumped. But because in circuit analysis we lump components into very idealistic models, we're not going to worry about regions. We're just going to talk about points. So this node here is receiving it. There's a current I2 entering it, and I1 and I3 are leaving it. So what we would say is that, for example, so I1 plus I2 plus I3 equals 0. But we have to develop a convention here, and that convention typically is that the current entering the node is a positive and the current leaving the node is a negative. There's a negative sign attached to it. And we'll see that in a minute. But let's first talk about where this comes from. So we're not going to talk too much about the physics behind this because we've devoted the initial few lectures to physics, and now we're going to focus more on analysis and circuits and sort of high-level ideal models. So we're not going to delve back into the physics, but we're going to briefly talk about where this comes from. So the bedrock principle here, or the very low level, the fundamental principle this comes from is conservation of charge, which states that electric charges cannot be created nor destroyed. They can only be transferred from one place to another. So in this case, we know that current is the rate of change of charge. So what the KCL is telling us is that anytime you have a current entering, there's no buildup of charge at a given node. Otherwise, that would be sort of capacitive, if you will, and you would have voltages not matching, and we'll get to that soon. But to look at it simply, then this means that as the current enters, the same rate of change must be taken. Rate of change of charge must be taken out outside of that node, so that the law of conservation of charge is satisfied. Now, do keep in mind that these wires that we draw in circuit analysis, in the initial circuit analysis, are ideal wires with no resistance across them and therefore no voltage drop across them. If we needed to represent the parasitic resistance or inductance, for example, of wires, we would simply draw ideal wires with, let's ignore inductance. We're going to talk about that much later. Let's just say that there's parasitic resistance, some amount ohms per length, let's just say ohms per meter, because that's how you measure the resistance of wires. You go by a certain amount of resistance per unit length. So we would draw ideal wires and lump all of that resistance of that entire wire into a resistor, and then treat the rest as ideal. This is a very typical thing we do in electrical engineering and in circuit analysis, and it simplifies things and it gives you a clear picture of what's going on. So with those introductions now, I just want to really reiterate that what this means and why it's important and what the assumptions are here. So the assumptions are that, again, there's no voltage drop across these ideal wires, and that at a given node, you cannot have a charge buildup. Because if you had a charge buildup, then another node will have a different charge buildup, and then you have what's called a capacitor, or you could have a voltage drop across that wire. It just doesn't add up to the assumptions that we've made. And we'll get into more details and more examples later on, so I'm trying to give you the introductions here. Now let's talk about the proof for this. So let's just do a simple mathematical proof for what's been talked about here. Let's go up to the very beginning and move over. So before we get into this, remember that the current is the rate of change of charge per unit time, and charge is similarly the integral of the current from some time to another time, t1, of respective time. Now, recall from calculus that the rate of change of some function f, let's just say, for example, that f of x is equal to the rate of change of small f of x dx, then small f of x is equal to the integral of large f of x. That's the relationship that's being used here. So let's start with a term here called I total. That represents the total current in a set of branches. Let's just say there's n of them, but we'll write out the first few terms, so I1 through I3, we'll write that out. Now, if you take, based on this rule, if you take the integral of the current, we should get the total charge on the left-hand side. And due to linearity property of, it's an algebraic property, what's going to happen here is that we're going to take, the integral here is going to get distributed to every single term here. So we move over to the next step. So the integral of y1 plus the integral of y2 and so on. But each of these are the charges, the total charges, so q1 through q3. And that's from some time t0 to t1, but I'm going to exclude that for the rest of these and just say that's the total charge up to point t. And that t could be whatever value. So the total charge then is equal to the sum of the individual charges due to those currents. So this is telling us that this must be equal to each other, and that's where KCL sort of comes from if you want to look at it mathematically. Just to give you a very simple example then, if you have the currents I1, I2, and I3 in this manner, we can see that here's I, the value, here's time. We can see that as you go up higher here, the value increases. So let's just say, for example, this is 10 amps, this is 5 amps, and this is, for example, 3 amps. Then if you take the integral of this first function I1, we're going to be starting from 0. So the integral of that is, at that point, is 0. Then we keep on taking the sum of these individual chunks all the way down to the bottom here. We take uniform sums. I can't really draw that nicely here. And as we take these uniform sums, we're going to linearly keep increasing the value obtained at that point. So if you go up to the point, let's just say 2 seconds. If you go up to this point, we've summed up to 2 seconds. And let's just say that's here, 2 seconds. We've summed up all of those values, all those little rectangles up to this point, the Riemann sums. And that's going to give us the total charge at that point. And if you go to, for example, 4 seconds, then let's say over here, we're summing up more and more and more, and we get a larger value for the charge. Then if you look at I2, it has a smaller value of 5 amps, for example, and if we sum that up, we're still going to linearly increase the amount of charge, but then there's a smaller slope because there's smaller height to these Riemann sums, these Riemann rectangles, and so on and so forth for Q3. If you want to go in reverse, then you can see that if I take the rate of change of this value charge, so dq dt, remember that's the current, and if I take the rate of change, we can also see that this guy has a steeper slope or a larger value, and that's a constant here. That's a slope of 10. This guy has a slope of 5, and that's not to scale, but it's just an example. That's a slope of 3. So let's go on and talk about some of the practical notes in using KCL to solve circuit analysis problems. So as we saw in the beginning of the lecture, there's a relationship KCL, and it relates the total, the number of currents in each branch coming to a certain node, and it states that the sum of the currents must equal 0. But it's important to assign directionality to those currents because obviously in a given node, currents don't only enter or they don't only leave, they can enter or leave. And since we're talking about algebra, one way to distinguish opposites is to assign a plus and a minus sign. So in this case, you could say, make a convention up, and that's what's usually used, and they say that if a current is entering a node, it obtains a plus sign as a direction in the algebraic sum. and if it's exiting a node, it receives a minus sign. So in this case, so let's first say this. So it's important to note that it doesn't matter which sign you actually use. For example, if you say if it enters a node, the current enters a node is a plus, or if it exits a node is a minus, you can also just switch these signs and these conventions. What is very important is that you don't mix these up and you stay consistent. So if you chose this convention, any given current that is entering a node has to receive a plus sign, and any given current that is exiting a node should receive a minus sign. So let's, for example, look here. So I have a current I1 entering, so that should get a plus sign here. I have a current I2 leaving, and I got the colors mixed up, but you get the point. So I2 is leaving, so that should get a minus sign according to this convention up here. I3 is also leaving, and that should get a minus sign. But let's look here. So if I factor the negative sign out here, that's equal to 0. So factor the negative sign out, you get what? You get a negative sign multiplied by minus I1, because if I multiply this quantity out, I got to get plus I1 as shown up here. So you get a minus I1 plus I2 plus I3 equals 0. Now, you can also just sum I2 to both sides and add I3 to both sides, and you get I1 is equal to I2 plus I3. This is an important way of writing this because it's an alternative way to represent KCL. So it's, instead of saying, okay, we have n currents, so let's just go ahead and sum all the currents. We are now saying, okay, this current is entering this node. The only other place it can go to from this node is through I2 and I3. So the sum of the two currents I2 and I3 must equal what initially came to the node from I1. So this is a very important node that we're going to use, and we're going to use this way of writing KCLs to quickly go ahead and analyze circuits. If you're unsure about it, you can always start from the beginning and just say I1 plus I2 plus dot 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 plus IN is equal to 0, and just go from there. But this is now that we've observed what these mean and we've discussed some of the consequences of this relationship, we can just go ahead and from now on use this result and just say whatever the total current is entering a node, whatever is leaving is going to, let me say it in a better way. So whatever current is entering a node is going to equal the sum of the currents leaving the node, or vice versa. Now let's look at the other case where we choose the other convention. So we say that, let's write it here. So now we're going to say that, let's cross these out and say what is exiting. Let me write it with green. So let's just say now that what is exiting is going to get a plus sign. So what exits the node is going to get a plus sign, and what enters is going to get a minus sign. So if we use that convention just to demonstrate the point, we see that here, case 2, so that was case 1, this is case 2. In case 2, so we have a current I1 entering the node, but now that is a negative sign. So minus I1 plus I2, because it is now leaving, and the convention is that exiting is plus I3 equals 0. If you take I1 to the other side, we get the same result as above, which demonstrates that it doesn't matter what sign convention you use. What's important, again, is to use, to stay consistent and identify the directionality in such a way that whatever enters the node gets one sign, and whatever exits the node gets the opposite sign. I think I'll beat that point to death, so let's move on and just summarize that point. So the sum of currents entering a node must equal the sum of currents leaving the node. This is the alternative way of writing KCLs. Now let's go ahead and talk about Kirchhoff's voltage law, or KVL. This law states that if you have a particular closed system, a closed path, the sum of individual voltages in a given loop should equal 0. And the bedrock principle here is from conservation of energy. So energy cannot be created nor destroyed. All it can do is it can transfer from one form of energy to another, and it's going to get used up in some way, but it cannot be destroyed or created. So using that principle, the bedrock principle there, we say that in a given loop, the sum of every individual voltage drop or voltage rise must equal 0. And the way to indicate that mathematically, to represent that, you say the sum of from V sub j from j equals 1 to n is equal to all the individual voltages summed up and set to 0. You might be wondering how we get to assign the polarities of the voltages here, and how do we go about applying this principle. But in terms of the polarity, we'll see soon that regardless of what polarity you indicated, the correct answer will come out of the equations so long as you're consistent with your sign. And that this is a point that I'm going to repeatedly reiterate, because it leads to so many errors when you first learn it. And if you're careful with it, you can save yourself a lot of trouble and just do the problems correctly from the get-go. So as long as you stay consistent with your signs that you assign to these quantities, you should be good to go, and the correct polarity of voltage or the correct direction of current will sort of pop out of the equation, and I'll demonstrate that clearly in examples to come. So in this case, as we stated, that's what the law says here. The KVL says it's based on conservation of energy. Now let's go ahead and look at the consequences derived from KVL, some practical notes, that is. So KVL consequences, so we can go about this multiple ways. So we can either go clockwise to sum of the voltages, or we can go counterclockwise. Another important point is that whichever polarity is encountered first as we traverse the loop, that polarity is going to be assigned to the corresponding voltage quantity. So for example, in the first case here, we're going to go clockwise. So let's just start from any point here. I'll start from this node. And you can start from any point as long as you end at that same point. But I'm going to start from the one that I like here on the bottom left. So I'm going to start from this point and traverse the loop in this direction. That's the direction that I'm going through the loop. So as I go along that loop, I'm going to see, okay, from this point, I go up, I see V1. V1 though, I see the negative sign. As I stated here, the polarity encountered first is going to be a negative polarity, so I get a negative sign. So negative V1, I keep going up, I see V2, but then I see the plus polarity here. It's going to be a plus V2, I keep going, I go to V3, but a negative sign is encountered, so that's a minus V3. I keep going, I see a V4, but a plus polarity is indicated, and I end up at this point. So I've traversed the loop, and I have assigned the correct polarities here. So I say minus V1 plus V2 minus V3 and plus V4 equals to 0. Then I take V1 and V2 to the other side of the equation, and I get V1 plus V3 is equal to, let's see, yes, so V1 plus V3 is equal to V2 plus V4. Similarly, if I go the other direction, so let's clear these arrows and go the opposite direction. What I'm going to see here is that, let me just close that up. If I start from the same point, for example, and go the other direction, I'm going to see a minus V4, and I keep going, I see a plus V3, I see a minus V2, and I see a plus V1. I write those down, and let's see, the way I've written it is from the other side, but let's see, V3 I've written. Let me correct these polarities. So I started from negative V4, so I'm going to say, let me correct these really quickly. I start from minus V4. Let's write this in order. So minus V4. Then I go up and I see plus V3. I go up counterclockwise and I see a plus V3. I keep going further and I see a minus V2. That is a minus V2, and finally I keep going and I see a plus V1. Plus V1, that's equal to 0. I take V2 and V4 to the other side and I get the same result. So the important point here is that regardless of which direction you take in the loop and regardless of which point you start at, here's 2 points here. Let me just state it clearly. So you start at some point, but you have to make sure that you end up at that same point. So I could start from any one of these points in the branch and end up back on itself. That's one important point there. The second important point is that you can go counterclockwise or clockwise, but the important point is there to choose the correct polarity that you see first and stay consistent with that. So this is similar to KCL in that instead of saying the sum of the voltages equals 0, we now say this. Let's see, the sum of voltage drops in a closed loop is equal to the sum of voltage rises in that same loop. So as we went along and we encountered from here, for example, we encountered a rise, we encountered a drop from plus to minus, we encountered a rise from minus to plus for V3, we encountered a plus to minus or a drop. So what this is saying is that whatever the rises are in the loop, that should equal the drops, the voltage drops in that same loop. Okay, so now let's go ahead and see some more interesting results. So in terms of KVL, what if we have a bunch of voltage sources V1 to Vn connected in parallel? Can we have V1 be, for example, 10 volts and V2 be 20 volts? Well, according to KVL, for it to hold true, it requires that if you have voltage sources in parallel in such a manner that they be equal to each other. So V1 through V2 all the way up to Vn must equal some value V0. That is the only way that KVL can be satisfied, and we know KVL is a physical law that governs the behavior of circuits, and it's based on the conservation of energy, which is a very solid foundation in physics and engineering. So for that law to hold, the only way this can be possible is that all the voltages are set to the same value if they're in parallel. Similarly, for KCL, you can't have two or more current sources or currents in series unless they're equal. So if you have I1, I2, and all the way to IN, the only way they can be in series is that they have the same current. So I1 through IN must equal some value, say I0. That is the only way they can be in series. So with that being said, we covered a lot of material today, so I'm going to have to cut the example and quiz short and make it very simple. But in the next couple of videos, we're going to beat these problems to death and look at many examples of KCL, KVL, some circuit simulations, circuit simulator to get a feel for how currents flow. So in this video, I'm going to finish off with a very simple example. So in this example, it says find Vx and Ix. So Vx is defined with this particular polarity, and the current is given in this particular direction, and we have to find the magnitudes since the directions are given. So let's go ahead and find Vx. What am I going to do? I have two principles, I have two tools in my toolkit, plus Ohm's law, which is the third tool in the toolkit. But in this case, I'm going to use either KCL or KVL. Well, in this case, we can see that there is a loop, and if you don't see the loop, let me redraw this. It would look like this. It would be the voltage source, and let's see, plus, minus, and the way that would look is I have the resistor here. Instead of saying grounding both ends here, I'm going to connect them to each other. That's equivalent because they're at the same potential. They're grounded, so they're at the same potential. And I'm going to ground this node here so that it looks more like a loop. But from now on, I'm not going to do this anymore. I'm just going to do it one time to demonstrate what I mean here. The plus is here, the minus is here. That's the polarity. It's called Vx. And the current is flowing in this direction according to that polarity. So how do we go about this? So we're going to say here is one loop. I'm going to go clockwise just for fun. That's what I like to do. I like to go clockwise. I'm gonna start at this point and I'm gonna go clockwise. So I'm gonna see what? I'm gonna see a negative 20 volts. Negative 20 volts. And I'm gonna keep going and I'm gonna say plus a Vx. And I'm gonna end at the same point. And what I'm gonna get is a plus Vx is equal to 0. Or if I take 20 to the other side, I'm gonna get that Vx is equal to 20 volts. Extremely simple. And you might have been able to tell this by just looking at it, which is a good thing. And it's a very simple example. I just wanted to apply KVL in a very simple case so that to justify something we already know, which is that the entire 20 volts here should be dropped across this resistor and give us the current Ix, which by Ohm's law, if you recall, V is equal to IR, and the current I is equal to V over R, which is equal to 20 volts over 10 ohms is equal to 2 amps. So Ix is 2 amps. Again, very simple. Just to complete the cycle, let's just say, as a bonus, what's the power? So, and then I'm just going to say power dissipated across the resistor, just to get more practice. So power dissipated would be either V squared over R or I squared R. And that would be equal to V squared, which is what? Which is 20 volts, so that's 400 volts squared per 10 ohms, so that is 40 watts. The current is 2 amps, so 2 squared is 4 times 10 ohms, so 10 amps squared times 10 ohms equals to 40 watts. So that is the power dissipated across that resistor. Now let's go on and talk about the quiz. Very slightly more complicated than the previous one. In this problem, I'm asking you to find V1 and V2. Use the principles learned here. So go ahead and give it a try, and I will solve the problem afterwards. Okay, so assuming that you've given it a try, I'm going to go ahead and do the standard thing. So I'm going to start here. I'm seeing a loop here, and there's the same current flowing through everything, so I'm not going to apply KCL. I would only apply that if I have multiple branches that are in parallel and not in series. Since I have the same current I, let's just say that's I, I'm going to go ahead and use KVL because I'm interested in finding the voltages. So I'm going to start from this point and go clockwise. So I'm going to label this as KVL and go ahead and write my first equation, which is something we should get used to. We should start doing it something like this. So as we get to more complicated circuits, we're going to see more and more equations. So let's just go ahead and learn to organize it nicely. So I'm going to say it's a KVL, and it's the first equation. So I'm going to see a negative 10 volts. Negative 10 volts as I go up. I'm going to see a plus V1, and I'm going to see a minus V2 as I keep going in this direction, minus V2. That is all equal to 0. Now if we solve this, we're going to get that V1 is equal to V2 plus 10 volts. Now we also know simply that using Ohm's law, we know that we have two resistors in series, so you have 3 ohms and 7 ohms, that's 10 ohms. If I want to find the current I would get I is equal to the voltage, which is 10 volts, over the sum of the resistors, which is 7 ohms and 3 ohms. That's going to give me 10 over 10, which is 1 amp. That gives me the current. And then we also see that the way I and the voltages are defined here, we would say that V1 is equal to I times 3, or 3 times I. That's going to give a plus sign because it's going from high potential to low potential. And we also see that V2 is equal to 7 times I, the current through it, times the resistance. But then this one's, the current's going from minus to plus, or low to high potential in this direction, so we're going to say minus here. We know the current, so then we're going to go ahead and get the voltages. So V1 is equal to 3 times 1 amp, so that's going to be 3 volts. And V2 is going to be 7 times 1, but then there's a negative sign, so that's going to be a negative 7 volts. Negative 7 volts. Now let's see if this makes sense. Let's see if this makes sense. So let's rewrite the KVL, and actually let's just plug in right into here. So we're going to have negative 10 volts plus 3 volts minus, and then we're going to have a minus 7 volts because V2 is minus 7 volts. We're going to have that. That is equal to 0. So we're going to get, let me just not color that. So negative 10 volts plus 3 plus 7, so that's going to be let's see here, plus, so that's a plus there, that's going to be a plus 10 volts equals 0, or 10 volts equals 10 volts. So we know that the polarities are correct, the current is in the correct direction here, and KVL is satisfied and the voltages are found. This video has become very long, so I will see you guys in the next video where we will do plenty of more examples and see some simulations. Thanks for watching.